At this point I have to explain why we have different reactions, why there's Sn2 and Sn1 reactions. The reasons have to do with the kinds of things we're using to do these reactions. Now if we go back to here, let's figure out what a primary, secondary and tertiary carbon is. A primary carbon has one C attached to the C with the X group. Now the X group here is the leaving group. And these are usually alkyl halides we're talking about, but they can be other things as well. But the X group is the leaving group, and this has one carbon attached to it. That's primary. The other way you can look at it is the X group is on the end. The other one I want to point out is tertiary. That's when we have three carbons connected to the C with the X group. And these are the primary differences between Sn1 and Sn2 processes. Now the other thing I have to remind you of is what's going on with these carbocations. Now a primary carbocation is going to look like this. It's going to have a C with a plus and two hydrogens here. A secondary has a C with a plus and a C connected to the plus, and the tertiary has the two C's connected to the plus. Now it turns out the more C's we have connected to the positive charge, the C with the positive charge, the more stable it's going to be. And this situation where you've got two hydrogens connected to the positive charge is going to be very unstable. The reason that these tertiary C's, the ones with three C's connected to the C plus, are most stable is due to this phenomenon called hyperconjugation, where what's actually happening is electrons from the CH bonds are actually helping to stabilize the positive charge on the C that's next door to these bonds. Notice that when you've got two hydrogens connected to the C+, there's no bonds there to help stabilize that positive charge. So tertiary carbocations, these guys are going to be much more stable than the primary ones. Also remember what a primary and a tertiary look like as far as their structures go. In the case of an Sn2 reaction, we're looking at a one-step process because there's sufficient room for it to occur. The Cn- can come in and the Br can leave at the same time because we just have hydrogens connected here in the case of a primary alkyl halide. So primary alkyl halides will usually go Sn2 because there's the room for the Cn to come in and the Br to leave. The hydrogens don't really take up very much room. The other factor that will also force the Sn2 reaction, the one-step process, is the fact that this cannot form a stable carbocation. If it did try to form a carbocation, the Br would leave and you'd get a primary, which is very unstable. Looking at the Sn1 reaction, we're starting with a tertiary alkyl halide over here. This will go in two steps. The Br will leave first, forming a nice stable carbocation, and then the Cn- will come in after that. The reason that this occurs this way is because by the Br leaving we get a nice stable tertiary carbocation in the first step that can react with the Cn-. Notice also that there's insufficient room for the Cn- to come in here and kick this out at the same time. So that doesn't happen. The other thing we need to talk about with Sn2 reactions and Sn1 reactions is the different solvents that are used. If we're talking about an Sn2 attack, that is a concerted or a one-step kind of attack, where the Cn- comes in and the Br leaves at the same time, this will be supported by non-polar aprotic solvents. That is, solvents that are not polar, but don't have hydrogens on them. That's because this makes the Cn- more negative and allows it to come in and attack more quickly. So it makes the Cn- a more powerful nucleophile. In the case of Sn1 reactions, because we're getting that carbocation in that first step where the Br leaves and we get a C+, this C+ will be supported by polar solvents, protic solvents, solvents like water, solvents like ethanol, solvents that have OHs on them will be supported by the Sn1 reaction. Alright, so just to summarize what we came up with the Sn1 and Sn2 reactions. First of all, primary alkyl halides will tend to go via an Sn2 route. See, I've got the check mark here, because there's sufficient room for the Cn- to come in and kick out the Br. Also, you will not get the stable cation if you take the Br off first, so it will not go via an Sn1 process. Tertiary alkyl halides will go via an Sn1 process because you can get this nice stable tertiary carbocation by removing the Br and then having something else come in and attack the carbocation. There's insufficient room for the Cn- to come in here and kick out this Br, so that won't work in the case of the tertiary alkyl halides. So you won't see an Sn2 reaction occurring when you've got a tertiary alkyl halide. It'll only go via the Sn1 process.